Hi, everyone. Thanks for coming. So just to hopefully get you all to know us a little bit better, I'm Jatin. I used to work at Tesla, and before that, I was at Karma for a little bit, and now I live in Seattle and just make plugins and other sort of random audio software.
Hi guys, I'm Chris. I just graduated with my PhD. Let me know if you're hiring.
So all good, yeah. So we've got a lot to get through, so we're probably going to go a bit fast. So if you want to look at the slides to kind of go through in your own time, or if you want to look at all of our code, it's all in this GitHub repository. So there's a bunch of plots and things, and almost all of them were generated by the code in that repository. I'll leave it up for a minute so people can scan if they want. Okay. Oh, a couple more. Perfect. Awesome, great. Cool, so this is part 2 of a talk that I gave in 2020. At that time, it was just me. This time, we've got Chris, so it'll be better. And kind of the idea for that original talk was to talk about a bunch of different circuit modeling techniques. I kind of noticed that in a lot of more academic papers and things, people seem to have very strong preferences for what they thought was the best modeling technique. And I was kind of learning about all of them and trying to understand, like, well, what's better about this one or that one, or different ways of doing things. And so I wanted to kind of present them all and give people an intro to a bunch of different things. And so we covered a lot of things. We covered sort of white box versus black box circuit modeling. We talked about nodal analysis, wave digital filters, neural networks, and we used a bunch of example circuits from this guitar pedal called the Klon Centaur. And so the reason why I wanted to give a part 2 is, first of all, to go in a bit more depth on some of the things we talked about last time. So last time we were only able to talk about some of the more basic ideas with each of those modeling techniques. So we'll go a bit deeper today and talk about some extensions on things. There's also been a lot of new research in the last 3 years, especially around black box modeling techniques and some things that have kind of been advanced. And there's a bunch of new and interesting techniques, which is mostly what Chris is going to be talking about during his slides.
Yeah, and let me walk you through the circuit we're going to go through for today. So it's a tube screamer circuit, or Zen drive, and many other pedals. And basically what we have is an op-amp with a diode pair and a feedback loop. So we're treating that as one unit today.
Yeah. Yeah, and there's one kind of potentiometer, which is like the distortion. It's usually called the distortion knob. So there's that P1 there that's like a variable resistor. And we'll go through this in more detail as we keep going. So just kind of a short outline. I'm going to talk about nodal analysis and how to extend kind of basic nodal analysis to work for nonlinear circuits. I'm going to talk about wave digital filters and extending more like basic wave digital filters to work with multi-port circuit elements. And then
later I'll talk about neural networks and as well as Graybox models for doing stuff together with both white and black box.
Perfect. Awesome. So when we were talking about nodal analysis last time, we talked about doing a Laplace transformation of a circuit and using that to construct like a transfer function and kind of going between the Laplace domain and the digital domain, and then using this thing called the bilinear transform to go in between kind of the analog domain and the digital domain. And the problem with that is it only works for circuits that are strictly linear. So as soon as you have a nonlinear element, like in our circuit today, we have a diode pair, that kind of approach doesn't really work. And so this is something that people have been investigating for a while, like how do you break past that limitation? There's a bunch of methods. So the two we'll talk about today are the Nodal DK method, or NDK for short, and modified nodal analysis, or MNA. So modified nodal analysis, the term is used in a lot of different ways, but the way that the stuff that I'm going to be talking about today is something that I mostly picked up from listening to talks by Andy Simper and Eric Tarr and folks who have talked at ADC in the past. So maybe some of this will look familiar to you, which would be great. So we're going to start with like some circuit rules. If you've worked with analog electronics before, you've probably seen some of this. If not, it's okay. It's just some math. You don't have to worry too much about what it means. So we have what's called Ohm's law, which is like a relationship between the voltage and current going through a resistor. We have Kirchhoff's current law, which says that the sum of all the currents going into a node in the circuit has to equal 0. We have the capacitor voltage law, which relates the current and voltage going through a capacitor. And we have these op-amp laws for ideal op-amps. Obviously, things aren't always ideal in the real world, but to just keep things simpler for today, we're going to say that the voltage at the positive and negative terminal of an op-amp have to be equal, and the current going into your op-amp always has to be 0. So for the resistor, we have a pretty easy way to figure out the voltage-current relationship, and you can see there's not really any expression of time in that Ohm's law. But for the capacitor voltage, we have this idea of time and how the capacitor, what the capacitor does depends on what happened to the capacitor in the past. And so we have to come up with a way of discretizing the capacitor so we can use it in the digital domain. And to do that, today we're going to use the trapezoidal rule. There's other ways you could do it, but this is what we'll do today. And so the idea with the trapezoidal rule is it's a way of approximating an integral using some kind of fixed step in between points along your integral. And so if we just apply that rule to the the capacitor voltage law, then we get this expression here, where we can figure out the current voltage if we know the current and the previous time step, current and voltage. And this t over here is kind of our time step or our sample time. Then we'll come up with some intermediate names for things, what I'll call admittance and state. If you want to argue about the physical meanings of these things, we can do that later. And then we can end up with these equations. So we have sort of a voltage-current relationship. So if we know the voltage, we can compute the current. And then we need to be able to update the state so that when we process the next time step of our signal, we have an updated state. So we're going to go through these steps real quick with this positive terminal branch of the circuit here. So we know the current going through resistor 5 using Ohm's law. We have an expression for the current going through capacitor 2, again using the capacitor voltage law from the previous slide. And then we know using Kirchhoff's current law that the current going through capacitor 2 minus the current going through resistor 5 has to equal 0. So if we do a bit of algebra, we can solve for this V plus voltage. And the way we would go ahead and implement this in code is to basically just write down everything that we've written down here. So we have our capacitor 2 admittance, that's this GC2. This is just like a temporary variable to get rid of some multiplies. And then we have our capacitor 2 state. So we can compute V plus using the equation that we derived here. And then we can update our capacitor state using the capacitor update rule. And if we go and we run some audio through that, we'll get something that's not very interesting, but that's just because this small part of the circuit isn't very interesting by itself. As we start to build up the whole circuit together, it'll get more interesting. So we can do the same thing with this next branch of the circuit. I'm not going to go through the math again because it's almost the same, and the code again is almost the same. We have our capacitor 3 admittance, we have our capacitor 3 state, and then we do our computation and we do our capacitor state update. Now we get to the more interesting part. So we have our feedback path. Again, we can use Kirchhoff's current law to kind of relate the different currents going through this part of the circuit. So IC3, the current through capacitor 3, we computed on the last slide. But now we have this diode pair current, and that's going to be a bit more complicated. So we have Shockley's diode model. There's other diode models too, but this is the one we'll use today, which is basically a relationship between the diode pair voltage and the diode pair current. And so if we basically plug this into our KCL equation along with the capacitor and resistor currents that we got from our other laws, we end up with this big equation. And basically, we want to solve this for the diode pair voltage, since that's the quantity we care about at the moment. The problem is this is what we call an implicit equation, where you can't just solve it directly. So in this case, we're going to use an iterative solver to solve this equation. There's a bunch of types of iterative solvers. Today, we'll use a Newton-Raphson solver. Again, if you want to talk about the details, we can do that later. So the way a Newton-Raphson solver works is you write down a function called f that is equal to 0. And in this case, we can do that just by rearranging that IC3 equation from above. And then you need to compute the derivative of that. I'm not going to go into the calculus of it, but it looks like that. And then the way you do a Newton-Raphson solver is you start with some estimate for your quantity, and then you keep going over and over, updating that estimate until You say, okay, that's close enough, we'll consider it correct. And then you stop iterating. And so that's kind of the update rule there at the bottom. So again, we can do this in code. So again, we've got our capacitor for admittance, our capacitor for state, and our voltage across the diode pair. You don't need to keep the diode pair voltage as like state, but I like to do it to help make the initial estimate for the iterative solver a little bit better. And then this is the iterative solver here. So we've got our function f, we've got our derivative of f, we've got the amount that we're updating our estimate by, and then this is where we actually update the estimate. And then you say, okay, when are we done iterating? Well, either when delta gets very small or when we've used too many iterations. So we don't want to just spin on this forever if we're not really getting closer. But usually that means there's some other problem. So hopefully you're not hitting that case. And then again, we update our capacitor state. So if you put all this together, so the all three kind of branches of the circuit, you can put it all together into a complete implementation of this circuit model. And it looks something like this. And if you really want to get fancy, you can use SIMD to optimize it. So that's an exercise for you all. Have fun. And if you go through and run some signal through it, you'll get a result something like this. So you get kind of this wave shaping distortion that sounds kind of interesting. And you can see as we change the value of the P1 resistor, we get a slightly different shape. So next we'll talk very briefly about the Nodal DK method. So it's short for Nodal discrete K method. The K method is something else that we're not going to talk about. And this was worked on a lot by David Ye back in maybe 2005 to 2010, along with some other folks at Karma. And the notation that I use mostly comes from this paper by Holters and Zolzer in 2011. And if you've heard this name Nodal DK before, that's because Daniel is around here somewhere. There he is. Yeah, he did a presentation or a poster about this in 2019 and sort of showed his framework for doing this. So yeah, I won't go in too much detail, but basically the way you do a nodal decay model, you start by labeling things. So you go through your circuit and you assign a number to each node, and then you kind of write down, like for your input voltage, it goes from node 1 to node 0, which is ground, so it's kind of fake. And then like resistor 5 goes from node 2 to node 6 and things like that. Then you make what I call them layout matrices. I don't know if there's a better name, but the idea is that you have all these matrices. So this is the matrix for resistors. And so each row corresponds to a resistor, and everything in the matrix is either 0, +1, or -1. And so you have a +1 or a -1 depending on which nodes your resistor goes between. You do the same thing for your capacitors, your voltage sources, and so on. And you also need to do this for your kind of output voltage nodes. Then once you have those layout matrices, you can plug them into these fancy equations and you wind up with these ABCD matrices. This is what the math looks like, but you'll probably want to go through it more slowly later. And then you end up with this state space system. So you have a way to update the system state, you have a way to compute your system output, and you have a way to compute the nonlinear components of your system. And again, for the nonlinear components, we're usually going to need an iterative solver, maybe a lookup table, something of that sort, to be able to compute those quantities. So this is what your code might look like. This is what my code looks like. It's a little bit messy, but I'll talk about why it's that way in a second. So this is the iterative solver. It's almost the same as what you saw on the previous slide. Now, the problem with trying to use a lookup table for something like this is that your inputs to your lookup table is not just one value. It could be 3 or 4 values. I think for this circuit, it would end up being 4 values. And for larger circuits, the number of inputs to your lookup table will get bigger and bigger. And so for a lookup table with 4 inputs, you need a 4-dimensional table. And so as you keep adding dimensions, things kind of get to the point where they take up a lot of memory. And so it might not actually be faster than doing an iterative solver just because of all the time you're spending looking through different parts of memory. And also you could just run out of memory on your system and then it's not possible at all. Anyway, then you can compute your outputs and your state update and you've got your full model. Now the reason why that code looks so messy is because it's actually auto-generated. So I don't really like writing that kind of code by hand, so I have this little system that takes a JSON configuration like this, and it spits out the code for me. And so that's kind of why it's nice to know if a voltage source is fixed or if a resistor is variable or something like that. So I have these extra annotations in the net list there. I was hoping that my code generation system would be ready to share today, but it's not. So maybe sometime later this year, it'll be ready to share. Oh, and again, if you go through and put some signal through this model, you get kind of the same looking wave shape. So just to recap on nodal analysis, you can use nodal analysis for nonlinear circuits. You just need to kind of extend it with these different types of methods. I've only talked about NDK and MNA, but there's several others. Now, you kind of might notice that if you want to model a circuit this way, you kind of need to know about traditional circuit analysis, things like netlists, voltage laws, current laws, things like that. And you're almost always going to need an iterative solver or something in place of the iterative solver if you have nonlinear elements in your circuit. So now we're going to move on to wave digital filters. And so last time at ADC 2020, we talked about WDFs, and we talked about what I'll call traditional WDFs. So the idea with wave digital filters is that instead of kind of coming up with your circuit model and discretizing it all together like you usually do with nodal analysis, you discretize your individual circuit components, and then you can kind of plug them together with chunks of code. And I'll show what this looks like in a second. Now, for traditional WDFs, you need to be able to decompose your circuit into series connections and parallel connections. So things like op amps that have multiple ports kind of make that impossible, and we'll see an example of that in a second. Traditional WDFs also require that your circuit has no more than one nonlinear element. We're not going to go past that today just because of the example circuit we chose, but there are ways to go past that with more modern WDF techniques. And so this is kind of the idea here. You've got like a capacitor and a resistor, and they're kind of separate from everything else. And then you've got this, what we call an adapter. So this is a series adapter. So basically what we have here, we have a capacitor in series with this resistive voltage source here. This is a parallel adapter, diode pair, things like that. So you kind of have to decompose your circuit into these series and parallel junctions to be able to make a traditional wave digital filter model. Sorry. So to go beyond traditional WDFs, we have this thing called an R-type adapter. This is something that Kurt Warner did a lot of research on in the 2010s. If you go read his DAFX papers, IEEE papers, his PhD dissertation, you'll get to know all the nasty details and all of the different ways you can use R-type adapters. And so the kind of fundamental change here is that instead of thinking about everything in our circuit either being in series or parallel, we're going to use this thing called an SPQR tree. So S is just series, P is just parallel. Q is this thing that I've been told I should never have to worry about, but ask Kurt if you want to know more. And then R is what we call a rigid node, which is poorly defined in my opinion. It's basically any node that's not SP or Q is R. And so this is the way that I think about it. So when we have a wave digital filter adapter, basically we have all of these waves that are going into and out of each adapter. So like this series adapter here, it's got a wave coming in there, a wave coming in there, a wave coming in there. And then we've got these waves coming out, right? So a wave going out there, a wave going out there, and so on. And so the scattering matrix basically routes the waves between the different ports. You have 3 incoming waves, 3 outgoing waves. You take your 3 input waves as a vector, you multiply them by your scattering matrix, you get 3 outgoing waves. And so the way you determine your scattering matrix coefficients is by looking at the impedances of the ports that are facing your adapter. And so usually we have one port that we want to make what we call reflection free. And all that means is that the scattering matrix along our diagonal is going to have one element that is 0. So if the first port is reflection free, the top left diagonal value of our scattering matrix is going to be 0. We'll see that in a second. So for series and parallel adapters, we kind of have these very basic scattering matrices that we can reuse again and again and again in every version of a series or parallel adapter. But for R-type adapters, we kind of need some custom scattering matrix that we need to be able to create for this particular circuit topology. And if we go to a different circuit topology, we'll need a brand new scattering matrix and a brand new R-type adapter. So this is the way that I choose to go about making an R-type adapter. Again, if you want all of like the theory on how and why these work, go read Kurt's papers. That's really the best resource. So I start by kind of grouping circuit elements into these groups, which here we have A, B, C, and D. And the idea is that any two circuit elements that you can combine in series or parallel can go in a group. So for example, group C is resistor 4 and C3. These are in series with each other, so we can put them in a group together. Similar with like the diode pair and capacitor 4, they're in parallel, so they can be in a group together. And that's how you create these groups. Then we need to label the nodes in between the groups. So here we have just 4, 1, 2, 3, and 4. And then we'll make a net list, but this will be different from the net list we had in the Nodal DK part of the talk. Here we have a net list that's just for the R-type adapter. And the idea is that every group we can replace with this thing called a Thevenin equivalent circuit, which is just a voltage source and a resistor in series with each other. And again, this can get kind of hairy to think about if you like really think about it too hard. So I try to keep it really simple for myself and have this kind of cookbook approach. So the way I think about it is we have port A going from node 3 here to node 4 there. So I'm going to write down a voltage source and a resistor, and I'm going to have them start at node 3 and 4, and I'm going to have them end at some node that I don't have a name for yet, so I'll just call it X. Then we can do the same thing for group B, group C, group D. These goes from 1 to 2, 1 to 3, and so on. And then now I can go back and I can fill in those X's with these virtual nodes, and I just count up from the highest node that we were at before. So before the highest number node was 4, so now I'll just count up 5, 6, 7, 8, and I'll just fill in these columns 5, 6, 7, 8, and 5, 6, 7, 8. That ends up getting you your Thevenin equivalent thing, but you don't have to think about it too hard. You just write down the numbers in order, and it's not too bad. And then at the end, we'll add in our op amps. So the particular way that you're going to do this might depend on the way you choose to have your op amp model in wave digital filters. The one that I need here, or the one that I'm using here, has 4 nodes, so you have plus, minus, out, and ground. So turns out pretty easy. So now we need to actually derive our scattering matrix. So when we go and do this, first thing we want to make sure we're doing is telling our scattering matrix generator that we want to make group A a reflection-free port, and that's just because that's the one that contains our nonlinear element, which is the diode pair. And then to actually do this, I have one tool that I wrote that's written in Python using this weird Sage math system that will generate a scattering matrix. Now I usually use this other one that I wrote in Mathematica. It's kind of weird. Sometimes the Python one is faster. Sometimes the Mathematica one is faster. I don't really have a reason why. But yeah, this could take 10, 20 minutes. I usually just turn it on and go have lunch or something. And then when I come back, it's got my matrix ready for me. And so this is what your scattering matrix will look like. So you can see here, because we made the first port reflection free, we've got a 0 up there. And then this ends up being a 4x4 matrix, but the rows are really long, so I just chop them off at some point. And then you're going to have some expression for the adapted port impedance. And basically, that's the number that we chose for one free parameter that ends up making that top left value 0. And we're going to see how this gets used in a second here. So now we can actually sit down and write some code. And so we want to say, okay, well, I want to use a wave digital filter library, so I don't have to write my own. I don't know which one to use. So when I started doing this, there was this library called RTWDF, which is written in C++, written in 2016 in C++. And in RTWDF, your circuit model is actually defined at runtime. So what that means is you can kind of change how your circuit is built at runtime. So if you have a resistor and you want to make it a capacitor, you can do that at runtime. You could replace your resistor with like a whole other network of components. All that stuff is possible at runtime, which isn't really possible with the MNA approach, or you have to kind of do it differently. You have to rebuild your whole circuit model instead of just swapping out individual components. So that's kind of cool that you can do that. But we'll talk in a second about why you might not want to. So then in 2021, there was a library in Faust called WD models that was written. And in WD models, you have to define your circuit model at compile time. There's not really a way around that. But then I ended up writing my own library. That's also in C++, and you can kind of choose. You can do your model at runtime or compile time, and it's up to you. And so if you're wondering what's the fastest, well, generally it's the compile time ones are the fastest. And that's just because the compiler is able to see ahead of time, like what math are you trying to do to actually implement your model, and it can kind of bust through a lot of virtual function calls and things like that. If you were at Gustav's talk yesterday, you'll kind of know more or less why. And so I ran these benchmarks just by making a few different circuit models, playing 1,000 seconds of audio through them and timing how long it took. And generally, my library is pretty fast when you use it in compile time mode. But for some models, the Faust library ended up being better. So I guess I have some more work to do. Anyway, so this is how I would make this circuit model using my library. So for group B, you can just write down your capacitor and your resistor and your parallel adapter. And then I have these like combined elements, which for some reason the compiler is able to optimize a little bit better if you kind of pre-compute two elements in series with each other. So that's what I'm doing there. And then this is how you kind of implement the R-type adapter. So this is kind of this funky template pattern that Eyal Amir showed me, if any of you guys know him. So we have to kind of define this impedance calculator for our R-type adapter before the R-type adapter itself is defined. So we have this template fake type for our R-type adapter, but we don't know what it is yet. But we know that we're going to be able to get the port impedances that are facing the R-type adapter. So we're going to need these to compute our scattering matrix. We're also going to need these parameters for our op-amp model, which those can just be constant. But now, once we need to update the impedance of our R-type adapter, we can compute our scattering matrix. So this is the one we generated a couple slides ago using Mathematica or whatever. And this is a lot of math, but you only have to do it when you're changing your resistor values or when you're setting the sample rate of your model or things like that. So if you had to do this every sample, it would be pretty expensive, but because we're not doing it that way, it's not too bad. And then you also need to compute your adapted port impedance and whatever. And then at the end here, you can define your R-type adapter using the impedance calculator that we just set up. So now we have our wave digital filter implementation. And again, you get the same kind of wave shaping distortion. Looks about right. So just to recap WDFs, we can handle any linear circuit topology if we're using R-type adapters. And we can resolve up to a single nonlinear element without an iterative solver. So that's kind of a nice benefit relative to the nodal analysis approach. That said, if we add more nonlinear elements, or if we're starting to mess with nonlinear elements that have multiple ports, so transistors, triodes, and so on, then you usually will need an iterative solver. So you only get to live in the good life for a little bit. And now we've got Chris to do the second half.
Thank you, Jatin, for the exceptional walkthrough for the white box methods. Now I'll talk about black box models and later on Graybox models. So in the interest of time, I will go quite fast as we have a lot of ground to cover. So in part one of this talk, Jatin spoke about these neural network architectures, namely the WaveNet, TCN, RNNs, and STNs. And I'm sure by now we're all rather familiar with them due to their widespread success. I'll do a very general overview of them. So the WaveNet and the TCNs, they use convolutional, dilated convolutional neural network layers in order to capture more temporal information. And recurrent and state transition networks, they use some sort of feedback mechanism or memory in order to encode or learn more temporal information about sequences. And so on this slide, we showcase some available audio products that we know utilize neural network technologies. So the last on this list we are aware uses convolutional neural networks. These are some updates for everyone about what was mentioned in 2020. The idea was that neural networks were not so easy to implement in a real-time environment. However, not only that, we knew that there were issues with sample rate and control parameters. We also, with RT-Neural, you can train your model with your favorite Python library, either TensorFlow or PyTorch. And we hope to support more in the future, maybe MXNet or something. And use the train weights in real-time audio code. Thank you to the other talks for mentioning us as well. On top of that, we want to show that there is a way for the system to cope with sample rate differences and hope to approach sample rate invariance. This is the plot showing the good results of the RNN. Next, I want to speak about something called lactose, the linear array of conditions, topologies with separated error pack propagation. Thank you. So lactose stands with the group of other models under the conditional models umbrella. And in the interest of time, I will speak about the main point, namely that there exists a case where if the if statement is not differentiable, this is solved by splitting each condition into individual models and then training them with a special training graph. So the other advantage here is that instead of having one gigantic model, that you are then enabled to encompass lesser parameter space, so the model bounds less. In practice, you can see the graph and the pseudocode on the right here. The model checks the condition and loads the model weights into the model shell. Inference and backprop, and the whole dance is done. And the new model weights are then saved and tested, and the next samples tested with the conditions. This same procedure can be implemented for real-time inference just without the backprop and optimization step. For example, here, we use this piecewise linear function as our target, and we compare lactose with a model that's bigger by 1 order of magnitude. So here are the results. We can see that from the graph, the lactose model can even model the signal better than larger networks. What's interesting here is that with RT-neural implementation, the models are blazingly fast, with like 500 times real time. And yep. Just pause for a while. All good? Yeah. Next is the ever famous or infamous transformer model. So I won't speak too much about transformer model. I'm sure we can read the Attention is All You Need paper. However, I will mention that encoding might be a problem in real time as well. So maybe we need something like gzip in less is more. So our very, very tiny transformer, around 100 parameters I trained, as compared to our usual 7 billion or 13 billion parameter transformer friends. You can see the expected behavior is not too well, right? But the literature tells us that we usually, this architecture fares better with a higher parameter count. However, I will comment that the transformer model probably has the generative ability to learn multiple types of distortions with the same model. Next, I'll speak about Graybox models. So as a short introduction, I want to mention DDSP as a Graybox model as well due to explainability. But the important point here is I propose, and I credit this to Johann from NI, this graph of explainability against abstraction. So on one side, traditional white box models are very explainable, but they're very manual because there's quite little abstraction, right? And then on the other side, black box is not so explainable, but it's very highly abstracted. So I think there's an interesting area in between these two where you can find models that sort of balance between explainability and abstraction. So if we take lactose as an example, the conditional statements give the user the ability to explain the system with conditional statements. Or conversely, we can learn more about the system based on how the model resolves those conditional statements. So by applying different conditional statements, we can learn more about the model. In this section, I will cover symbolic regression, as well as differentiable wave digital filters, physics-approximating neural networks, and this waffle technique. So firstly, see this will play. Yep. So symbolic regression is a technique that allows a genetic algorithm to discover innate operator structures of the system. It is one of the techniques that does not rely on a predefined model architecture, but instead learns and converges towards a model with low loss using allowed operators and functions that are designated beforehand. In this example, we used the PySR library and the credits here to make the model. The results here show that this model had this particular model, because it spits out a couple of different models at once, and that has the lowest loss among the few models that it gave us. However, symbolic regression can be a bit finicky and might not give you the expected result unless some conditions are met, such as having adequate constraints or other such things. I want to comment that on the counterfactual nature of these systems, since I highlighted the explainability of Graybox systems, symbolic regression allows us to discover the physics of a particular system. This has proven useful in other fields like astrophysics and so on. Next, I speak about differentiable wave digital filters. As a quick overview, we showed that a circuit like this, a diode clipper, can be expressed as a tree structure. And what we can then do is replace the nonlinear element, or in this case, the diode pair, with a new trainable neural network, and then place this whole structure inside the trainable graph. That way we can propagate the inputs up the whole training graph, compute the neural network, do the backprop, and then come out of the graph and test for loss. Yeah, we can talk more about the details later. This was presented in the talk last year by me, so I refer you to the archive for more information. Here are the results. Note that the difference comes from the model being trained on real-world diodes as opposed to the Shockley model as shown before. Counterfactual information here can be assessed based on the type of model used and how well this model resolves. In short, recurrent models do well. It means it signifies time-based nonlinearities, and if convolutional model does well, then it points to state-space interactions in the nonlinearity. I have presented about physics-approximating neural networks before, and I refer you to the original ACM paper about the topic. The main consideration here is that we tend to think of neural networks as function approximators under the universal approximation theorem. This is not always true. Non-time invariant functions are not memoizable, and networks trained on a discretization space and then inference on another one are examples of this violation. Instead, we can imagine an extremely nonlinear function being a function carrying a family of functions. I'll call it mathcal f. And this family of functions contains individual functions, small f, that are dependent on hidden variables and states. So what neural networks allow us to do is model each small function f in the family of functions as a self-optimizing branch of the neural network. This way, the operator defined the definition of the operator structure will act as a regularization of the neural network, meaning that better operator structures will result in more regularization, increasing the likelihood of convergent search. I use the example of a nonlinear capacitor from the paper. This physics model is converted into an operator structure like so. With this, the trained model does much better than a regular neural network on this problem. We can see here that the error is much lower than both the regular neural network or a linear model that assumes no nonlinearity. On the counterfactual information this provides, we can explain more of the system depending on the success of the operator structure. This lends itself very well to genetic algorithms, such as the one shown before. Lastly, I want to speak about WDF, which stands for Wave Digital Domain Autoencoder Shaped Networks for Fast Learning and Emulation. Thanks. To sum up, this model uses the conversion to the wave digital domain as a form of feature analysis for the networks, as well as physics-approximating neural networks to resolve the physical measurements of the components. These are then concatenated to with a set of trainable ports interaction parameters to mimic the WDF structure of the R adapter. I refer you to my thesis for more information about this. I'm happy to discuss more afterwards. I want to showcase the effects of these ports interaction parameters, showing that indeed it functions well as parameters of the system. I want to invite Jatin now to continue the presentation.
Cool. So I kind of wanted to just go back and go through with a bunch of these different approaches, what kind of performance we were able to get as far as a real-time performance. And so what we're seeing here is basically how many of these models could be run in real time at, I think we're doing 96 kilohertz. Mm-hmm. And so something that's kind of interesting is that the white box models are generally performing a little bit better than our recurrent neural networks. And the nodal analysis, or the modified nodal analysis model, is actually a little bit faster than the wave digital filter, even though it is using an iterative solver, whereas the wave digital filter doesn't need one. But some more general kind of things to think about are that white box models can be very fast. So I've heard people say sometimes that white box models are too slow. really it depends on the circuit and the technique you're using and all that. So it's kind of hard to make general statements like that, but it is possible for white box models to be very fast. With black box models, you can get really good performance, but it really depends a lot on the size of your model. So a large black box model will be slower, a small black box model will be faster, but then you have an accuracy trade-off, of course. With gray box models, you'll usually wind up somewhere in between. And again, you have to think about kind of a speed versus accuracy trade-off there as well. And it really depends a lot on the particular circuit you're modeling. So some circuits can be modeled very well with a small neural network, but maybe you would have a lot of trouble using a white box model that could be performant for that same circuit. So it really depends on the particular circuit and the particular accuracy that you're trying to achieve. A few other things to think about as far as accuracy versus speed trade-offs. If you're using an iterative solver, kind of think about what do you consider as a successful solving of that equation and kind of the constraints around that. For all of these models, you'll usually have some kind of math functions that you're going to want to do approximations of. So you can do a very high quality approximation that'll be slower than a very rough approximation. And for black box models, neural network size and things like that are really kind of where your accuracy versus speed trade-off is going to be the most obvious. So a few kind of general takeaways. We were talking about white box circuit modeling techniques. So these can include MNA, NDK, wave digital filters, and there's a ton of others too. So if you're interested in this, there's Port Hamiltonian models, there's the nodal state space approach, and a few others that I haven't talked about. For black box modeling techniques, we've talked about neural networks, specifically convolutional, recurrent, transformers, and conditional models. But there's also plenty of other approaches with Volterra kernels, dynamic convolution, things like that. So this field really goes as deep as you want it to go, and depending on how much time you have to read papers all day. And then for gray box modeling techniques, we've talked about symbolic representations, integrating neural networks with white box techniques like the differential WDFs. We talked about physics-approximating networks. And this is a very active research area. So people are coming up with new ways to do gray box modeling all the time. And it's a very exciting time to be doing this kind of thing. A few more general points. So oftentimes I get questions like, I have this circuit, what modeling technique should I use? And this is a very difficult question because it really depends. So a few things that I usually think about are, well, what kind of circuit is it? Does it have linear components, nonlinear components, feedback, no feedback, things like that? Do you want to be able to tweak and modify the model? So if you're training a black box model, you usually won't be able to tweak it after the fact. You have to kind of retrain it with some tweaks done to the hardware that you're training on or something like that. Whereas with a white box model, it's usually very easy to tweak and change your model afterwards. Think about your accuracy goals and your performance goals. Some kind of general advice that I usually think about is that for all modeling techniques, a small model can be very fast, but to get your model small usually takes a lot of effort. And this is true for black box models and white box models as well. A lot of people who do black box modeling seem to not really want to learn much about circuits. I say the better you understand your circuit, the better model you'll get, regardless of what technique you're using. I think that's really important. And then also think about what you want out of making a circuit model. Do you just want something that sounds cool, or do you want to learn more about circuits and learn more about the substance that you're working with? I think that's important as well. And finally, I think a lot of people in circuit modeling are very obsessed with, I can get, a little bit more accurate model of this circuit or that circuit. It sounds much closer to the real thing. And that's great, but it's also important to think about making something new, right? Like sometimes I'll have a model of a circuit that isn't very accurate, but I think it sounds different in some cool and unique way and maybe has some different places where I could control how it sounds. And I think that's really cool too. I think it's important not to get too stuck in just trying to recreate something that already exists, right? Like the person who made the Tube Screamer didn't just keep making the Tube Screamer, they started making other pedals too. So, make something new and hopefully, you enjoy that part as well. So yeah, thanks all for coming to this talk. And I'd like to mention that we're sponsored by RT Neural. Yeah.